Okay, so here's part 3 of applied functional analysis practice final exam number 8. Let h equals L2, 0 to 1. Consider this a of x equals negative f double prime of x with the following domain we're given. Show that a is symmetric, show that a is positive, solve the eigenvalue problem here, determine all eigenvalues and eigenfunctions, show that the eigenfunctions form an orthogonal basis and for here, and explain how spectral decompositions are used in solving evolution PDE. So I'm going to go through this part rather quickly because my apologies, losing my voice a little bit due to allergies. So our spectral theory in Hilbert spaces. Here's part A, just glossing over it. For this inner product is equal to this integral here, this negative f double prime of x, g of x bar dx. Not all of this steps are shown, but if you integrate by parts, you're going to get the following. Okay, and since g of 0 is equal to g of 1 equals 0, the boundary term vanishes, and you wind up with this inner product equals this integral. And similarly, this inner product equals this integral from 0 to 1 f of negative g double prime bar dx equals this integral 0 to 1 f prime g prime bar dx. So A is going to be symmetric, and one of the reasons is because this inner product AFG equals inner product of FAG. Okay, so now we'll move along. Second page, B, C, D, F. Okay, so for this, okay, positivity, we take f equals g, then this inner product equals this integral here greater than or equal to 0, and from this we can conclude that a is positive. For the eigenvalue portion of the problem, we're going to solve for negative f double prime equals lambda f is the following. Here are boundary conditions that are implied. Thus the only 0 exists, so lambda 0 is not an eigenvalue. If lambda was less than 0, we write lambda equals negative mu squared, and then f double prime equals mu squared f, so that we get f of x equals ae mu x plus be negative mu x. Boundary conditions would force f equals 0, so no negative eigenvalues. If lambda is greater than 0, we write lambda equals mu squared, and then f double prime plus mu squared f equals 0. General solution given here. Those are mu's. From f of 0 equals 0, a equals 0, and then f of 1 equals b sine mu equals 0. For a non-zero solution, b cannot equal 0, so sine mu equals 0. So mu equals n pi, where n is 1, 2, 3, 4, on and on and on. Therefore, lambda sub n is n squared pi squared. For part D, our eigenvalues and eigenfunctions, the eigenvalues are lambda sub n equals n squared pi squared, where n equals 1, 2, 3, 4, 5, on and on and on. With eigenvalues here, phi sub n of x equals sine of n pi x, and a normalized eigenfunction is e sub n of x equals root square root of 2 sine n pi x. Part E, orthogonal basis, the sine functions form the standard Fourier sine basis for that L2 0 to 1. They are orthogonal because of this integral being equal to 0. When n does not equal m, and they're complete in here, so every f such that it's an element of L2 0 to 1 can be expanded by this series with convergence in L2. And that's a C sub n, E sub n. For partial differential equation use, for the heat equation, one expands that u of t comma x, and then you get this n equals 1, this sigma n equals 1, infinity going to infinity, c sub n e to the negative lambda sub n t, e sub n of x, and since lambda sub n equals n squared pi squared, we could conclude that high frequency modes decay rapidly. Very important. And this is central in deterministic and stochastic partial differential equation analysis. Okay, so that's number 8. Moving along to number 9. Okay, Fourier transform methods here. Go through this quickly. Let f of x equal e to the negative a times absolute value of x, where a is greater than 0. Here are a, b, c, d, and e. Okay, so for number 9 here, Fourier transform methods, we're given here. Here's our element, f, the element in here. Compute this integral, negative infinity e to the negative a to the absolute value of x dx, split it up into 2 components, and it's just single variable integration here. So 1 over a plus 1 over a equals 2 over a, and we get that norm of f else 1, that's going to equal 2 over a is less than infinity. So since that's less than infinity, we could conclude that f is an element of that L1R. For part B, Fourier transform using this f hat of xi equals this integral here. Should look very familiar. F hat of xi equals this integral, split up, negative infinity to 0, e to the ax, e to the negative I, psi x dx, plus 0 to infinity, e to the negative ax, e to the negative I, psi x dx, and that's just going to come out to very nicely 1 over a minus I xi plus 1 over a plus I xi. And for part C, if we simplify this, if we add these two, we're just going to wind up with f hat of xi equals 2a over a squared plus xi squared. And then moving along to D and E. Okay, for D and E, for the decay, okay, we get the following as absolute value of psi goes to infinity, f of xi, that approximates 2a over xi squared. Therefore, f hat decays like xi, absolute value of xi negative to negative 2. This decay reflects the exponential decay of f and its limited smoothness at x equals 0. And our partial differential equation relevance, Fourier transforms convert differentiation into multiplication. Okay, so here we're given the rules that are very famous and explicit for Fourier differentiation for f prime and f double prime there, hat and hat respectively. So linear PDEs with constant coefficients often become algebraic or ordinary differential equations in the Fourier space. Okay, so moving along to number 10. So we're given this Heaviside function, very famous. Show that h is not classically differentiable. B, using these test functions, we're going to compute that h prime phi. Show that h prime equals delta, where delta is the Dirac distribution. Compute the weak derivative u of x equals absolute value of x. And explain why distributions are useful for PDEs with singular sources. And please forgive me for my poorly drawn delta and some of my very poorly drawn variables. Sorry about that. So, or I should say phi. Some professors say phi. I'll say phi here. Okay, should be phi for this context usually. And part E, I don't know if I said it. Explain why distributions are useful for PDEs with singular sources. Okay, so distributions and weak derivatives for part type problem. Part A, classical differentiability H is constant on these intervals. So its classical derivative is 0 away from 0. But h jumps at 0, so it is not classically differentiable at 0. For part B, distributional derivative. Okay, by definition, this relies on definitions. We get the following for these h prime, inner product h prime, phi equals negative inner product h, comma, phi prime. Since h of x equals 0, for x is less than 0, and h of x equals 1, and for x is greater than 0. This inner product h, phi prime, equals the integral of from 0 to infinity phi prime of x dx, and since phi is an element in this c sub c infinity r, phi x goes to 0 for large x. Therefore, we get this integral 0 to infinity phi prime of x dx equals phi of infinity minus phi of 0. And that equals 0 minus phi of 0 equals negative phi of 0. Thus, this inner product here equals negative of negative phi of 0, which at the end becomes equal to phi of 0. Very interesting problem. Sorry if I mispronounced anything there. Moving along to C, D, and E. Okay, so identification with delta. The Dirac delta distribution satisfies this inner product. Delta phi equals delta of 0. And since that inner product h prime phi equals phi of 0, we get h prime equals delta. Very elegant. Weak derivative of u of x equals absolute value of x, and classically u prime of x equals this piecewise function. So this is the sine function, u of x equals that SGN sine x, in the weak sense that absolute value of x, that prime, equals SGN of x. And the second weak derivative is the following, that's equal to 2 delta. PDE relevance. Distributions allow one to handle singular sources such as point charges, impulses, shocks, and measures. For example, Poisson's equation with a point source is naturally written as negative delta U equals, that's delta. This has no classical right-hand side as an ordinary function, but it is meaningful distributionally. Okay, so my apologies, my voice is going. And for the last one, number 11, let H be a separable Hilbert space and let K be the following, be a compact self-adjoint operator. State the spectral, for A, B, C, respectively. State the spectral theorem for compact self-adjoint operators. Show that every non-zero point of the spectrum is an eigenvalue. Discuss why the compact operators arise naturally in integral equations and finite dimensional approximations of PDEs. So compact self-adjoint operators, so spectral theorem. The spectral theorem for compact self-adjoint operators says that there exists an orthonormal basis H, possibly after including a basis for the kernel of K, consisting of eigenvectors of K. The non-zero spectrum consists of real eigenvalues of finite multiplicity, with only possible accumulation point being 0. Part B, non-zero spectrum consists of eigenvalues, but lambda not equals 0 belong to the spectrum of K. For compact operators, any non-zero spectral value cannot belong to the continuous spectrum in the same way it can for general bounded operators. The compactness forces approximate eigenvectors that have convergent subsequences, and suppose there exists a sequence U sub n with this norm, U sub n equals 1, and then we have this norm of that K minus lambda I, U sub n go to 0, and then K U sub n minus lambda, U sub n approaching 0. Since K is compact, This K U sub n as a convergent subsequence, and along that subsequence we get that lambda U sub n equals the following difference. That also converges, and since lambda cannot equal 0, U sub n has a convergent subsequence. So letting U sub n here, arrow U, then that norm of U equals 1, and we get the following product equals 0, and hence Ku equals lambda U. So lambda is an eigenvalue. And last, for letter C here, why compact operators arise. So compact operators arise naturally from the integral operators such as this, that K, that this Kf x, that omega K x y f of y dy. They also arise in PDE theory because elliptic solution operators often improve regularity. And for example, solving that negative delta U equals F usually produces a more regular U than F. And when embedded back into a weaker space, this smoothing often gives compactness. In numerical methods, compactness is related to why finite dimensional approximations can converge, and bounded sets of approximate solutions have strongly convergent subsequences after applying smoothing operators. Okay, so that's all. That's parts 1, 2, and 3. And my apologies. My voice is, my allergies are bothering me today. So my apologies if I misread anything. The math's okay though on the paper. Thank you very much, and have a great day.